everyone! Welcome back to Cody's Lab. So today I'm going to be testing a rocket that uses metallic sodium and water as propellant. I actually bought this sodium about 5 years ago for this project. Fortunately, the mason jar has kept it rather well. You can see it's still quite shiny. And the reason I wanted to do this with sodium is, well, sodium is actually a pretty cheap material to make as long as you make it on site. It's really a transportation cost that's expensive. All it takes is sodium chloride, salt, and electricity. And the chlorine that is released can also be used for other products. So it's actually could be a quite abundant material. But also, it's fairly energy dense. The energy density is about the same as some high explosives like TNT. About half if you include the weight of the water, of course. But it does also release that energy spontaneously on contact with water. All right, go ahead. And further, the main product of the reaction, sodium hydroxide, will react with water and carbon dioxide in the atmosphere to form sodium bicarbonate or baking soda. So it is virtually non-toxic. And also, the particles of this is very small, and so if they're high in the atmosphere, they will take a long time to settle out. In that time, they will reflect sunlight, thus increasing the albedo of the Earth, and perhaps, if there's enough of it, help with climate change. So, in principle, it could be the perfect rocket fuel. It doesn't require any igniters or anything special, just put the water to it, and it'll burn. So, today we're going to test that out. Unfortunately, I haven't been able to actually get permission to launch a rocket. One of the major hurdles I'm running into is one of the requirements is that the rocket contain no metallic components. And if the fuel's metal, that's straight out. It requires special licensing right away. So we're not going to actually launching a rocket. If it flies, I will have failed spectacularly. We're going to try not to do that. We're just going to do a bench test. And really the idea is to see how effective of a rocket fuel it is. What is the impulse that it can provide? So I've got a test stand set up. Whoop. Let me get my camera off. As you can see, I've got the test rig set up here inside the mine. That is so that if something gets loose or explodes, I've got lots of soil to contain it. The test rig is mostly a long pipe with a fulcrum in the middle and a spring scale at the end. So when the rocket thrusts upwards, it'll pull down on that scale and we can measure the thrust. I've got a dash pot here so that the shocks, any sudden changes will be smoothed out. This is the cable which will be igniting the motor. This is a fulcrum which is made out of a wheel, and I can loosen these and I can move this back and forth to change the lever ratio. The fulcrum is currently in the middle, so any changes on the scale will be 1-to-1 to the amount of thrust that the motor is producing. If I come over here, see there's a weight, which is to balance the rig and also to pre-tension it. Over here, you can see I've got the camera set up onto the spring scale, and it's inside of a box, so if it gets really smoky, you'll still be able to see it. The view won't be obscured. And I'm actually going to open this and turn on this camera now. Let me turn this on. Okay, recording. I've got it set up on the scale. Let's close this back up. Looks like one of the wire ropes came off. Let's put that back. There we go. It's about 5 pounds worth of pre-tension on there. That's to further help dampen out vibrations. So let me come out. Ooh. See, I got this all wired up. We're going to use a little model rocket engine to test the test stand. So this cable goes out 100 feet, so I can launch it from way over there. I'm not in direct line of sight with the rocket, so I'll be safe. Plus I'm wearing armor. We're just gonna set this camera up right here, maybe zoom in a little, and we can observe the test. So this is a test of the test rig. I'm gonna go touch the wires together. Touching wires in 3, 2, 1. That didn't seem right. I think my model rocket motor exploded. Perhaps the maybe I crushed it when I was clamping it down. Anyway, I guess I'll let the smoke clear and we'll try that again. Okay, test of the test rig, take 2. Touching wires in 3, 2, 1. There we go, that sounded much better. Excellent. I'll go review the data from that. So I've made a graph of the amount of force in pounds over time in frames. Now to find the impulse, I need to find the area under the curve. Now an easy way to do that is just trace the graph and then cut it out and weigh the paper. Yep. So I need to find the mass of a known area of paper and then compare it to the weight of the cutout piece of graph. It's a lot faster than adding up the squares, at least. And this piece here I need to subtract.
You should write on it that it needs to be subtracted.
Okay. Another thing, the mass of the engine decreased over time. So this over here, when the engine stopped firing, is actually 0 thrust. So I just approximated this as a straight line, assuming the engine lost mass roughly at the same rate. So started out at 0 on the scale and then ended up with 0.5 pounds. Okay, so the mass of 100 square units of paper, which should be 0.1 pound seconds per unit, is 229 milligrams. Now, I'm going to take my little piece that was below 0 on the graph, drop that on the scale, tear that out. Okay, now I can remove it. So that's negative 11 milligrams or so. I'm going to put on the rest of the graph. I got 314 15 milligrams. So 314 milligrams divided by 2.29 milligrams per square is 137 squares. Now 1 square is actually 0.05 pound seconds. I was looking at this, my scale is 0.5 pound increments. So 0.05 pounds seconds per square times 137 squares is 6.86 pound seconds. Now 1 pound second is 4.45 Newton seconds. So multiplying those together, we get 30.5 Newton seconds. Now an E-class model rocket engine should produce between 20 and 40 Newton seconds, so that's right in the middle. So that is pretty good. There are, of course, some sources of error. One of the main ones is the fact that this spike is probably too high and this spike is probably too low because the device used to measure the force was just not dampened well enough. The actual graph probably topped out like this and then went down more like this, right? But you'll notice that if you take this piece, put it in here, take this, put it in there, it's going to be roughly the same as the area that I showed. So the error is not huge. So now that I've shown that my measuring device can give me at least an idea of the impulse produced by a rocket engine, it's time to put together the actual sodium water rocket. All right, here is the finished rocket. It's all put together, mounted to the test stand, and waiting to be fueled. It is made almost entirely from off-the-shelf components that I purchased from the hardware store, pipe fittings and such. The only things I had to modify special was a couple of fittings here, which I had to weld together to make the injector holder, and a block of graphite, which I machined to make the nozzle right there. So let me run through the design real quick. So first of all, there's a tube of copper here, which will be used to send pressurized gas to pressurize the oxidizer tank. The oxidizer, of course, being water. I've got the long tube like this because I want to be far away from this when it's got any sort of pressure in it. The only time I want to be next to it is when there's no pressure. This is just to add safety. So this is a 100-foot long copper tube, which I'll pressurize from outside the mine. So I'll put the water in there. I'm going to use just some pure water. People have suggested I use like peroxide or something, but for this first test, it's just going to be straight water. So that'll be in there. There'll be some gas on top of it, which will push it through this pipe, and it'll meet this valve. Now this valve is opened with a spring, and to keep it from being opened, I've got a string which will be melted by this wire running an electric current through this little piece of nichrome. So that'll melt that string, and that'll open this valve very quickly. The water will continue through down to here, meeting the injector, which is just the tip off of a wand of a pressure washer. And then that will spray water into this combustion chamber, which will be filled with sodium. There's none in there right now. I'm currently thinking of just putting like a hollow cylinder of sodium inside of here, and the water will react with it. It's basically a hybrid rocket. That'll make sodium hydroxide, hydrogen, probably some steam from unreacted water, and that'll come out the nozzle, hopefully producing thrust. I am about to run a test with just water to mostly check for leaks and make sure everything works. So I'm going to add about 500 milliliters of water into the water tank. There we go, there's the water. Now, just because it's made out of pipe and will probably explode does not mean it's a pipe bomb. Intention matters. Okay, pressurized water test. Okay, so this is what I'm pressurizing the rocket with. This tank of argon. I'm using argon because, well, that's what I had. And it won't react with the sodium, so that's good. Okay, so gonna add some pressure. It's gonna be hard to fill with that long tube. I want to go with a rather high feed pressure so that the engine is less likely to sputter, but also I don't want to burst the copper pipes. so I'm shooting for between 500 and 1,000 psi. All right, so it's about 800 psi of argon. I'm just gonna touch the wires to the battery. Stick that one there. There it goes. Yep, no more pressure. And I can, of course, relieve any excess pressure by opening that valve. There's a wet spot on the ground. I think it worked. Okay, so here's the graph of the water-only test. Something I forgot to mention earlier is that the camera is recording at 30 frames per second, so 30 frames is 1 second. And I've marked out the seconds here. The water was coming out of the engine for just over 5 seconds. So in the beginning, when the valve opens, we get some shocks like that, and then it dampens out to about 0. And it holds at 0 for a while, then it shoots up to about a quarter, holds there, and then it shoots up to half a pound, about, and it stays there clear to the very end. When the gas starts coming through, then it shoots up to a little over a pound, and then it comes back down to 1 pound, and then it reads constant as nothing's coming out of the engine. This here is just the amount of weight that the engine lost. Remember, the engine losing weight reads as a positive on the scale, so it looks like it's got thrust, but it's actually just the weight lost of the engine. Now, I suspect that the engine actually lost weight pretty much continuously following this dotted line here, but the spring scale was reading kind of jagged like this, and I think that's just friction in the setup. So it took a little bit to get it to like kind of pop and move to what it was actually should have been reading, right? And the gas coming out at the end might have made a little bit of thrust. That's why it went a little bit above 1, but that's a tiny amount of thrust there. It was basically just enough to get the scale to, overcome friction and start reading its actual value. So yeah, the water coming out of the engine didn't make any thrust, which is what I wanted to show with this test. There it is. Let's go fill that up with sodium. Okay, weight of the combustion chamber without the sodium. 1.176 kilograms. So the plan for adding the sodium is to carefully melt and pour it a little at a time around a central rod. If it ignites, catches fire, I think I'll just step back and let it burn. It has a pretty low melting point, so hopefully this goes well. I'm going to try to keep it very close to its melting point and keep it under oil as much as possible. Okay, I'm going to pour the first batch in. It's going to go everywhere. Okay, I think that went relatively well. Let me melt a little bit more. There it is. full of sodium. Just let it cool. While it was cooling, I lit some sodium on fire to see how it burns. Makes a rather pretty orange color, and this is certainly a fire you can't put out with water. It's still a little warm. I can handle it now. Let's see if I can remove this rod. Oh yeah, easily. I could probably do that with my fingers. It's just gonna take a long time to get the all thread to come out. There's gonna be a little bit of weight of the mineral oil that will mess with the calculations, but I think it's gonna be small compared to the amount of sodium. And the mineral oil is definitely needed to keep the sodium from oxidizing. Hopefully the water can get into it quickly. Should have got a drill or something for this. Okay, there it is. Got the rod out. Oh, stuck to my magnet. There's the central hole. I'm just going to wipe it all down with this rag to remove excess oil and little bits of sodium. And with the sodium, the weight is 1.373 kilograms. So there it is. All the wires and everything have been removed. And I've kind of flared the sodium at the top out a little bit, hopefully to make the water go in a little easier. You can see the nozzle's not obstructed. Very good. I wonder if I can look down in there. Maybe. Yeah. So it's 197 grams of sodium. Let's go put it into the engine and see what happens. So there it is, the sodium. I'll load this onto the rocket. I'm going to be using 500 grams of water again. I think this will be an excess. I'm going to have the engine thrusting into a pan of vinegar. This is to absorb sound energy and also to help neutralize the alkali that'll be formed by the engine. Alright, so this is the final test. Hybrid rocket engine, 200 grams of sodium as fuel, 500 grams of water as oxidizer, pressurized 800 psi with argon, and the nozzle diameter opening is 1/4 inch. Touching wires in 3, 2, 1. Well, it ignited. That's quite the cloud it made. Let me turn this camera off. So here's the aftermath. It smells like vinegar. So it definitely made thrust, but it looks like very soon after ignition, the sodium melted and got shoved out unreacted. So most of it just burned in my pot of vinegar here. Everything's got a thin coating of something on it, so I'm gonna give it a good rinse. I'm gonna open it up and see what it looks like inside. See if there's any unreacted sodium. Okay. Actually, looks to be quite a lot of unreacted sodium. Something. There's the injector. Put that down in the vinegar. This, though, I might be able to recover some of the sodium. So there's the nozzle, completely unharmed. And here's the combustion chamber. You can, if you look down in there, you can see a little bit of sodium left up at the top. So I forgot to measure the weight of the combustion chamber before melting the sodium out, but I did save the sodium, so it's not a total loss. I'll just have a little bit of oil weight. So that's 70 grams of sodium remaining. So I'm analyzing this video frame by frame to see what happened, and the first thing I notice is the spring actually comes off the wire before the valve fully opens, so it only gets about halfway open, which fortunately is enough for the water to go through and the rocket to function, but that's something I'm definitely going to have to work on if I do another rocket. Also, you notice that the thrust seems to go negative. I think a lot of that is the recoil of the spring flipping up. And as the spring comes back around, now it's pulling down and it's adding thrust, as you can see there. But right here, the water hits the sodium, and it's starting to produce some gas, and we're getting some exhaust, and the thrust rapidly increases. It peaks at about 8.5 pounds, which is pretty good, but right here you can see some bits of sodium is already entering the exhaust, and as the amount of sodium increases, the thrust rapidly drops. And it's pretty wild from there, going up and down as pieces of sodium are entering the exhaust. It kind of managed to stabilize at about 4 pounds of thrust, but yeah, it's just burning very inefficiently. It's just sputtering. And then right there you can see the thrust basically goes to nothing. I think there's still water coming out, but there's not a lot of sodium being burned actually in the engine. Yeah, I think I saw some last drops of water right there. And here you can see there is no water. So I think the water did shut off sooner than the first pressurized water test. That could be the injector maybe moved a little bit when I was screwing the combustion chamber on, so it was open a little bit wider. It's not a big deal. The bigger deal is the sodium that got squirted out and is burning outside the engine. So yeah, from there we got no more thrust. That's just the end of it. Okay, here's the graph. Ignore this little mistakes here. As you can see, the thrust is all over the place. And once again, I'm approximating the loss of mass of the rocket, the zero line of thrust, moving up at a constant rate. I know it didn't, but I don't know the actual number, so I'm just going to have to guess and say that it was constant. So here we go. It ends up with a 1.5 pounds less weight than we started. That's about right, because I had about a pound of water and about half a pound of sodium. Okay, so let me cut out the graph and try to get the impulse out of this. Once again, I've tared the scale with the bits that were below zero. And now I'm going to weigh the bits that were above. So there we go. 300 milligrams. So, time for the results. 300 milligrams of paper, 2.29 milligrams per square, 131 squares. One square, of course, is 0.05 pound-seconds, so I used the same scale. 0.05 times 131 is 6.55 pound-seconds of total impulse produced by the engine.
And converting to newtons for you that like the metric, that's 29.1 newton seconds. Back to pounds. 6.55 pounds seconds divided by 1.5 pounds of fuel. That gives us our specific impulse. The pounds cancel, so it doesn't really matter what unit I'm using here. It gives me 4.68 seconds. And theoretically, if I wouldn't have used an excess of water, if I would use as minimum water as I could have, it would have ended up with about 6.55 seconds of specific impulse for this engine, which is abysmal. Black powder rockets typically do about 50 to 80 seconds, and the space shuttle got over 400. So this number is going to have to go up significantly before this is a viable rocket fuel. Thing is, though, this was a very inefficient burn. I think I could improve this substantially.
So there it is, my first attempt at a sodium-fueled rocket. By the way, this weighs over 11 pounds fully fueled, so if I had released it, it would have never even moved. So I will definitely come back to this project in the future and see if I can improve it. I think one thing I'm going to do is abandon the hybrid rocket design and move to a fully liquid-fueled rocket, perhaps using a liquid sodium-potassium alloy instead of a solid fuel grain. So anyway, that was a lot of fun. I learned a lot. Hope you enjoyed. I'll see you next time.